In this video, we are going to do some more stoichiometry practice, working with a balanced chemical equation. So here it says, plants convert carbon dioxide, water, and energy from the sun into sugar and oxygen gas in the process of photosynthesis. So got our chemical equation. It says, is this equation balanced? Now, we're not going to worry about this word energy in here. That's just kind of reminding us, hey, it gets energy from the sun. We're just going to focus on balancing the atoms, so let's use that same approach. So we have carbon atoms and hydrogens and oxygen in this equation. And if you look closely, this almost looks like a combustion reaction in reverse, because here we've got something that you could call a hydrocarbon reacting with oxygen, making CO2 and H2O. So the strategy that I encourage, where you just focus on first the carbons, then the hydrogens and the oxygens, we can use that same strategy here. But we'll also use the column to kind of keep track of what we see on both sides. So first up, I've got one carbon on the left from the CO2, and then I've got two hydrogens from the water, and I see three oxygens total on the left side. On the right side, we've got 6 carbons and 12 hydrogens, and then there's actually 8 oxygens. So step one, let's just balance the carbon. So you think about, where would you need to put a coefficient to make the carbons balanced? Well, we've got 6 here on the right side, and we've just got 1 here in front of CO2. So if we put a 6 in front of CO2, that's going to make the carbons balanced. And let's quickly update our count for oxygen, because that's what we should do every single time we do this column method. I recommend you update the count for all of the elements, at least check it. So here we've got 6 times 2 plus the 1 over here, so that's 13. All right, step 2 when balancing a combustion reaction is just do the hydrogen. So we've got 12 hydrogens right there, and we've got 2 right there. So if I could put a 6 here, then that would give us 12 hydrogens on the left to match with the 12 on the right. So that becomes 12. And let's update our count of oxygens on the left side. So we have 12 there and 6 there. So that brings it up to 18. So now step 3 says balance the oxygens, where if you need to use a fraction right here in front of the O2, that's okay, because you can always multiply everything by 2 to get rid of the fraction. Now, we have, or rather, we want 18 oxygens on the right side, and we already have 6 from the sugar molecule, so I'll do minus 6, so that equals 12. And then since oxygen is diatomic, I'll divide that by 2, and 12 divided by 2 is 6, so putting a 6 right here makes it all work out. So that's our balanced chemical equation. We've got a 6, a 1 in front of the sugar, and then another 6. Now, the whole reason why we did that is because we need the balanced chemical equation in order to do the stoichiometry in later problems. So next it says, how many grams of sugar are produced from 1,000 grams of water? So we're going to start off with the 1,000, 5 sig figs there, grams of H2O. And it is asking for grams of sugar. We're starting from grams, and we're trying to get to grams. So we're going to need 3 conversions, because we're going from grams of H2O to moles of H2O to moles of the sugar to grams of the sugar. So first we'll use the molar mass of the water. So molar mass of water, you get the molar mass of hydrogen times 2 plus the molar mass of oxygen. So looking over at our periodic table, 1.01 times 2 for the hydrogens, plus a 16 for the oxygen. So the molar mass of oxygen is essentially 18. So 18 grams of H2O per 1 mole of H2O. Next, we want to use the mole to mole ratio. So we'll have moles of H2O for moles of the C6H12O6. That's our sugar. So we need to look at the balanced chemical equation. So scrolling up, when we balanced we had a 6 in front of H2O, and then we didn't end up changing the coefficient in front of C6H12O6. So it's just a 6-to-1 ratio. So for every 1 mole of sugar that is produced, 6 moles of water is required. And then lastly, we will do the molar mass of the sugar to go from moles to grams. So we'll have moles of C6H12O6 here, and we'll convert it to grams of C6H12O6. So molar mass of sugar, okay, that's a big molecule. C6H12O6, let's go over here, periodic table. So C6H12O6, so we'll have 12.01 times 6 for the carbon, 1.01 times 12 for the hydrogens, and then 16.00 times 6 for the oxygens. So if you do that on your calculator, you should get, let's see, I'm trying to find, where did I do that? Oh, 180.16, there it is. I knew I did it ahead of time. 180.16 grams per mole. Okay, so that's the molar mass we're going to use. So 100, put it in this color, 180.16 grams per mole. Okay, so just checking our units just to verify everything canceled correctly. So grams of water is going to cancel with grams of water there. Moles of water is going to cancel with moles of water, and moles of C6H12O6 is going to cancel with moles there. So we're going to end up with grams of C6H12, which is what we wanted. So on your calculator, you do 1,000 divided by 18 divided by 6, and then times the 180. So on my calculator, I got 1668.148, and I'm writing more sig figs than I need on purpose. Since the 1000.0 had 5 sig figs, so all of those zeros count because that little decimal is right there, we're going to round this to 5 sig figs. So we're going to round it to 1668.1 grams, no, sorry, not grams per mole, but it's grams of C6H12O6. And just a quick note on the rounding. So if you had, for example, more sig figs when you pulled your molar mass, I just rounded it to 18. I was kind of being lazy. I discouraged that, but you might get a slightly different answer. So I think if you keep more sig figs for your molar mass of water, you might get 1667 or 1666. But just keep in mind that if you got an answer that's extremely close to mine, that's perfectly fine. You're still doing everything correctly. But sometimes, depending on exactly what you write for the molar mass, can have some difference on your final answer or due to rounding. Anyway, let's keep on going. So next one says, at STP, how many liters of carbon dioxide gas are needed to react with 1,000 grams of water? So again, our general strategy, we're going to go from grams of water, and we have to convert it to moles of water if we want to convert it to moles of anything else. So we'll go from grams of water to moles of water to moles of CO2. And then the last one, instead of going from moles to grams, we're going to go to liters. So from moles of CO2 to liters of CO2. And the conversion for that is 22.4 liters of a gas at STP equals 1 mole. So 1 mole of gas occupies 22.4 liters. So we'll start off with the 1,000 grams of H2O. And similar to the last one, we're going to use the molar mass, so 18 grams of H2O for every 1 mole of H2O. Then we're going to use the mole to mole ratio, so for however many moles of H2O to moles of CO2. So let's look up at the balanced chemical equation. For every 6 moles of water that react, 6 moles of carbon dioxide are also going to react. So we've got a 6 here and a 6 here. And then lastly, to go from moles of CO2 to liters of CO2, We were just saying it's 22.4 liters equals 1 mole. So every 1 mole of CO2 gas is going to occupy 22.4 liters. And that's only true at STP. So you got to make sure the problem explicitly says at standard temperature and pressure, because if it's at a different pressure or a different temperature, then the 22.4 equals 1 mole isn't true anymore. It might be way off or it might be really close, but this is only valid at STP. Okay, so on your calculator, you're going to do 1,000 divided by 18, multiplied by 6 times 6 is the same thing as like a 1-to-1 ratio, so don't have to type really anything there. And then times 22.4. So when I did that, and again, I'll be writing more sig figs just so we can round it, but my calculator said 1244.44 decimal repeating. So we want to round that to 5 sig figs because the 1000.0 that has 5 sig figs. So we'll round it to 1244.4 liters of CO2. Okay, for the last one, it says how many kilograms of carbon dioxide gas are consumed to produce 1 pound of sugar. So I'm going to start off. Now, fortunately, they told us, hey, 1 pound is 453.6 grams, so we don't need to do a pounds to grams conversion, thank goodness. But general strategy, and this one has one extra step because they are asking for kilograms of CO2, not just grams. But we're going to go from grams of sugar to moles of sugar to moles of CO2 to grams of CO2. And the last one that's new for this question, we're going to go from grams to kilograms of CO2. So starting off with the grams of sugar. So we have 453.6 grams of C6H12O6. And we will use the molar mass of C6H12O6, which we said earlier was 180.16 grams of C6H12O6. That's equal to 1 mole. So that's our molar mass. Next, we need to use the mole to mole ratio because so far our units are having us with moles of C6H12O6. So we need to convert from moles of one to moles of the other. So moles of C6H12O6, we're going to convert to moles of CO2. As for the numbers we write in there, we scroll up to the balanced chemical equation. So we saw that for every 1 mole of C6H12O6 that is produced, 6 moles of CO2 are going to be required. So those are the numbers we put in there. For every 1 sugar, we make 6 CO2. Okay, next, to go from moles to grams of CO2, we're finally going to use that molar mass of CO2. So for every 1 mole of CO2, and we're going to calculate it really quick, so let's go look at our periodic table. So carbon, 12.01, oxygen is 16, so you have 12.01 plus 32. So 44.01 grams of CO2 for 1 mole. And then the last one. So to go from grams of CO2 to kilograms of CO2, you should try to remember that kilo is 10 to the third. So that means that 1 kilogram is 10 to the third grams, which is the same thing as 1,000. So if we want to go from grams to kilograms, we put grams on the bottom, kilograms on the top, and there's 1,000 grams per 1 kilogram. So on your calculator, oh, and actually let's look at units one more time. So we saw that grams of sugar canceled, moles of sugar cancels, and then moles of CO2 cancels, and then the grams cancels and we get kilograms. So our final units end up being kilograms of CO2, and that's what we wanted. But anyway, on your calculator, you're going to do 453.6 divided by 180.16 times 6 times 44.01, and then divided by 1,000. And when I did that, my calculator told me 664.84, and the original problem gave us that starting value had 4 sig figs, and none of our other values really restrict us. So again, the molar ratio that's in here, that is like an exact quantity. So that's not going to limit how many sig figs, because it's exactly 6 moles of CO2 are going to react to make 1 mole of sugar. That's an exact amount. And then same thing for here. This is like a definition. It's exact. There are exactly 1,000 grams in 1 kilogram. So those do not affect the sig figs in your final answer. So we're going to do 4 sig figs. So that means we're going to round it to 664.8, and the units are kilograms of CO2.